So this video is on Stokes' theorem, and I've taken a quotation of the theorem. This is a very one of the big theorems in vector calculus. We've already seen Green's theorem, so I wanted to give you a full statement of proper formal statement of the theorem. So let's go through what it's talking about. So what it says is, let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation. And you remember what that is. So and a positive orientation is when you go around the curve and the region is to your left. So in other words, it's anti-clockwise oriented curve. Let F be a vector field whose components have continuous partial derivatives on the open region in R3 that contains S. So open region is one that, of course, as you know, the boundary is not included. Okay, that contains S itself. Then f dot dr, the line integral f dot dr of the vector field f is the same as the surface integral of the curl of S dot ds. So what Stokes' theorem is really doing is it's connecting the two ideas of saying that how we can take a line integral of a vector field and connect it to its surface integral, where we take by simply taking the curl of f. Now again, Stokes' theorem is mainly used, has one of its major uses is looking for shortcuts or simplicity. Because we're dealing with integrals that can be quite difficult to solve at times. They may be easy to set up, but may be very difficult to solve. Stokes' theorem just gives us another venue to try to evaluate the same thing. So let's look at an example of this. Now, keep in mind that when we calculate this, just as we've seen before, the curl of f, okay, dot ds is in fact what we've shown before in the earlier video, is that we take the dot product with the normal vector. So you need to keep this in mind because the example that I'm going to do will require you to understand that. So what we're doing is, let's look at a vector field and we'll calculate a line integral first, and then we'll using Stokes' theorem, and then we'll calculate a surface integral using Stokes' theorem. So here we want to calculate basically for f equals minus y x squared z cubed, and what we want to do is C is the intersection of the circular cylinder x squared plus y squared equals 4, and the plane x plus y z equals 3. So now what's going on here is that you have this, basically you've got a cylinder along the z-axis, okay? So this is what's going on, just to give you an idea. So there's a cylinder, and then there is the plane, this plane somewhat cutting it. And when it cuts it of course cuts it like this. So it's an ellipse. So it cuts it like at an angle. So in this, where it cuts it is it forms an ellipse there. Now that ellipse is this ellipse that I've shown here. I'm sorry, it doesn't look that good. Let me put it in red. So this ellipse is a little difficult to parameterize. So here it's even more pertinent to use Stokes' theorem because but it is easier to look at. For instance, the region, of course, the region here over which we're calculating this is a circle, okay, and that is x squared plus y squared equals 4, okay. But if we look at the plane, and if we look at the upward orientation, then your normal vector is going to be a unit normal vector, I should say, should be just the x derivative. This is our plane, so the x derivative of that will be 1, the y derivative is 0, and the z derivative is 1, okay, and that'll be divided by its magnitude, which is square root 2. So that's our normal vector. So now what we can do is, in fact, what it boils down to essentially is the following. So in this example, what happens is we are calculating the line integral is what we want to calculate, but we're going to use Stokes' theorem to do it. So S, okay, dot nds. Now here, this over the region R, we'll have 1 over root 2, and the cross product. I mean, and the cross product of nabla and f, which, so we need to calculate that. Sorry about that. So that actually works out to be just 0, 0, 2x plus 1. Okay, so you'll have what you'll end up with, and then we're going to have 0, 0, 2x plus 1. Okay, and dot product with 1, 0, 1 dA. So that will boil down to, now let's just do this. The region R that we're looking at is a circle with radius 2. So this is going to be 0 to 2 pi. Polar coordinates are best, and 0 to 2. But here, let me just show you, this will boil down to region R, 1 over root 2 into 2x plus 1, okay, into root 2 dA. Remember that that's writing into this S surface integral into a region, into a double integral, okay? We've shown that before. So that'll be square root 2 dA. If you're unsure of where I got this root 2 from, basically, if you remember, again, recall that the surface integral, okay, of f is ds, sorry, is region R or D, f, okay, and then you have the square root of the surface, zx or gx squared, or zx squared, sorry, plus zy squared plus 1. That means, so that means the x derivative is 1 and the y derivative is 0. So that will mean you'll end up with just square root of 2. Okay, so that's how you get that square root of 2. Now, so therefore, now as we parametrized it with polar coordinates, so we'll have this root 2 and this root 2 anyway will cancel. So it'll just be 2 times, so it'll be 2r cos theta plus 1. Okay, that's all we'll have here. Of course, we'll have r dr d theta. Okay, and that will work out. You can do that yourself. Simple stuff, enough integral, hopefully. That'll work out to be 4 pi. Look at this example. We want to calculate the curl of the surface integral of the curl of f, where f is as shown here, and s is the portion of the paraboloid z equals 4 minus x squared minus y squared above the xy plane, oriented so the normal vector point outwards to the paraboloid. So basic drawing of this would show something like, here's our paraboloid, and what's happening is your orientation is, this is your n, it's pointing outwards. So we need to keep that in mind as we continue to calculate. Of course, by Stokes' theorem, this can be written as the C, where C would be the boundary of this paraboloid, and that would mean, so it's the curve C, of course, and that essentially we're saying f dot dr according to Stokes' theorem. So that will work out to be integral over C of ez squared dx plus 4z minus y dy plus 8x sine y dz. Okay, parametrization of C will work out to be x equals 2 cosine t, y equals 2 sine t, and z equals 0. So that, which with t between 0 and 2 pi. So therefore, what will happen is we will have our integral is going to be from 0 to 2 pi. In fact, with single parameterization in t, so this will be e to the 0 is just going to give us 1, and the dx, remember, is going to be what? If you remember, it's x dash t, so it's going to be minus 2 sine t, and e to the 0 I'll put that here, e to the 0 minus 2 sine t dt, or the dt's will collect them at the end. Okay, and then we'll have plus 4z minus y, and the parametrized to be 4 times 0, z is 0, so nothing from there, just minus y, which will be minus 2 sine t. So keep it circular. Okay, so minus 2 sine t, and that will be multiplying y dash t, which is 2 cosine t. Okay, and the last one will be, in fact, nothing. It'll give us nothing, it's just 0. So that will work out, in fact, it'll work out to be 0. Okay, the answer is 0 in this case. So as you can see, we've gotten two examples. One example of Stokes' theorem to the curl of the surface integral as a line integral, and the line integral as a surface integral. So we'll stop here.